Hey everyone, and welcome to the first video of Lecture 10, which is the last lecture that we'll be looking at D-block chemistry in. And in this video, we'll be looking at crystal field theory in more detail and focusing on the octahedral and tetrahedral geometries and how their d orbitals are affected and what this means for their chemistry. So I'll start by giving a proper introduction of what crystal field theory is and how it works. I know I gave a brief one at the end of the last lecture, but that was just sort of an introduction rather than a real in-depth explanation. So with crystal field theory, it takes an electrostatic approach to the bonding and treats ligands as simple point charges. So in this case, the metal is positively charged, as it usually is, it's cation. And the ligands, rather than having any orbitals or anything, are just negatively charged points or spheres in space. With crystal field theory, we look at the interaction between these negatively charged points and the d orbitals of the metal. And I've got the d orbitals shown at the top here. And the interaction of the ligands, or these negatively charged point charges, with the d orbitals can affect the energies of the d orbitals. And we'll see this for various geometries through this lecture. And it's very good because it does allow us to work out why some complexes favour tetrahedral over octahedral and other electronic properties. But it is a bit oversimplified in some ways because it doesn't consider the orbital overlap of the ligand and the metal, because it doesn't consider the orbitals of the ligands at all, they're just point charges. And it doesn't explain something called the ligand spectrochemical series, which we will be talking about, but you don't need to know the background behind it. This requires additional theories that are more advanced, such as ligand field theory. Now let's start by looking at the octahedral complexes and what happens with crystal field theory here. So the first point is that in an isolated metal ion, the 5 d orbitals all have identical energies, or they can be called degenerate because they have the same energy. So that's why we usually draw the 3d orbitals when we're doing an orbital diagram. It's just like 5 lines, in a row. They've got the same energy. They've all got identical energies in an isolated metal ion. However, when it's in an octahedral coordination, they have separate energies, or 2 energy levels. 3 degenerate orbitals, which are referred to as T2G, and they're shown on the left here, and 2 degenerate orbitals, which are known as EG orbitals, on the right hand side here. And the reason for this is the interaction of the ligands with the various d orbitals. So we said in isolated metal ion, all the d orbitals have identical energies, but when we put this metal in what's called an octahedral crystal field, then we have the interaction of the point charges with the orbitals. So I've got the octahedral field, or the octahedral coordination sphere, shown for all of these here. So if you look at the T2G orbitals first, so these black spots are essentially the point charges. These are the ligands. And you can see that there is no interaction really between any of the ligands and these 3 d orbitals. Like the ligand just goes straight between any of the orbitals. And this means there's no interaction between the point charges of the ligand, which are negatively charged, and the d orbitals, which will also be negatively charged, remember, because they've got the metals electrons in. So this is why these go to a lower energy. So as shown here, dzx, yz, and xy go lower in energy. These are the T2G orbitals, and that's because there's no interaction between the ligand point charge and the orbital. If we look at the EG orbitals here, so these are the dz squared and the dx squared minus y squared orbitals. These do have an interaction with the ligands. So you can see here that with the z squared, the ligands coming from the top and the bottom go directly towards the vertical component, and those around the middle, the 4, are all interacting with this sort of donut shape in the middle of the orbital. So there's going to be repulsion between this d orbital, which has electrons in it, and the negatively charged point charges of the ligand that are coming. So that's why that's in a higher energy. And the same with the x squared minus y squared d orbital. They're completely facing or directly facing the negatively charged ligands. So that causes an increase in energy. So therefore the T2G orbitals are lower in energy, whereas the EG orbitals are higher in energy. And here we can see, the splitting of the d orbital, how it happens in this octahedral crystal field. So at the bottom here, we've just got the normal d orbitals in the metal ion, not the metal ion even, sorry, just the elemental metal. When it's put in what's called a spherical crystal field, so it's just negatively charged, sort of a uniform negative charge everywhere. They increase in energy, but they're all the same. And then when we actually introduce the geometrical crystal field, so like in this case the octahedral crystal field, the point charges, so the negative charge isn't uniform everywhere in a sphere. It's 6 point charges at the points of the octahedron. That's when the splitting happens. So you can see that the T2G orbitals, we said, were 3 that are all degenerate are lower in energy. This is because the point charges don't interact with these orbitals. And the EG orbitals go higher in energy because this is where the ligands are interacting unfavourably with the 2D orbitals. Now the difference in energy between the T2G and EG is referred to as the crystal field splitting energy, delta, and for an octahedral complex it's delta O, which just signifies the crystal field splitting energy of an octahedron, so O or oct for octahedron. And we can work out how much it's either stabilised or destabilised mathematically as well. So each T2G orbital, so the ones lower in energy, is stabilised by minus 0.4 times delta O. So minus 0.4 times the crystal field splitting energy of the octahedron. And the EG orbitals are destabilised by plus 0.6 times the crystal field splitting energy. And this is because the total energy has always got to be the same as it was before. We can't create energy out of nothing. So if you work it out mathematically, the total destabilisation, so 3 times the minus 0.4 of the crystal field energy, added to the total destabilisation equals 0. So we haven't made any energy or lost any energy. So that's why we get these values of plus 0.6 and minus 0.4. The crystal field splitting energy, this delta O, so the gap between the T2G and EG orbitals, is really important, and we'll see in the later slides and in the following videos that when we're adding electrons to these orbitals, it helps govern where they'll go. And it depends on a number of things. So it depends on the ligands. We've got this thing called the spectrochemical series, and I don't require you to know the order of ligands in the spectrochemical series. I'll give it to you in an exam if you need to know it. But essentially we've got what are called weak field ligands, which are down here, sort of the iodide and bromide, and they won't split these so much. And then you've got strong field ligands such as ammonia, CO, triphenylphosphine, and these cause them to split much bigger. And that's what I was saying on the first slide. One of the limitations of crystal field splitting energy is it doesn't explain why this happens. You don't need to know why this happens. But we do see this effect. So depending on what ligand it is, depends on how much the splitting energy is. And as I said, I'll give you the spectrochemical series in the exam. One important thing to note though is that this weak and strong is not at all related to the hard and soft acids and bases we saw in the last lecture. So if you remember, hard and soft acids and bases determined what metals liked to form bonds with what ligands. And you'll see there isn't really any correlation between the hard and soft and the weak field and strong field ligands. The other thing that can make a difference is the central metal ion. So its oxidation state makes a difference. So if it's a higher oxidation number, it will be a higher energy, which means these are further apart. And also which period or which row of the transition metals it's in makes a difference. So again, if it's in a higher period, if it's further down the transition metals, it will be a higher energy, therefore have a higher splitting again. Let's take a look at the tetrahedral complexes now in crystal field theory. These are slightly harder to visualize because none of the d orbitals point directly towards the point charges in a tetrahedral complex. So it's not like the octahedral one where either there's no interaction or a direct interaction. It's more like kind of touching a d orbital or quite strongly touching a d orbital. So I've got them here again. The T2, in this case, they're just T2 and E. There's no G label. So the G is just a symmetry label, much like you actually have with molecular orbitals as well. But I didn't go into the symmetry then. I don't want to go into symmetry now either. Just know that there's not this symmetry in a tetrahedral complex, and there is in the octahedral complex. So in the octahedral, you have this G notation, and in a tetrahedral, you don't. So in this case, we've got the orbitals again in this cube, and you can see the points here are on the corners that make the tetrahedron this time. So with T2, if we look at how the ligand approaches the metal, it will take this line, it's going to be quite hard to draw, from a point charge to the centre. And we can see this time it is actually touching this d orbital a bit, it is going towards it. The same with all of them. So with the YZ orbital, it's going towards the centre, but it will interact with this lobe a bit. And the same with the XY, it's going to the centre, but it's not going directly towards this d orbital, but it is going to be influenced by it. It's not going in between. So in this case, the D, XY, XZ and YZ orbitals actually point more towards the charges. So in this case, these are going to be destabilized a bit because of that interaction between the point charge and the lobe of the d orbital. Then if we look at the E orbitals, so the dz squared and x squared minus y squared, and look at the route these take towards the metal center. If you can imagine that, yeah, this one is now going more in between these lobes. So it's easy to compare this one with this one because it's just rotated by 45 degrees. You can see that with the XY, the ligand really interacts with this lobe. It's kind of pointing in a similar direction. Whereas this one, it goes in between. And the same with the Z squared. So this time it's kind of going in between the donut and the vertical component. So these have less of an interaction with the ligands, like these two orbitals, have less interaction with those point charges. And in this case, these are stabilized. So if we look at how this looks, with the d orbitals, this time we see that it's the other way around. The three degenerate orbitals, T2, are higher in energy, and the two degenerate orbitals, that are E, are now lower in energy this time. So it's the opposite of the octahedral geometry. So that's important to know and quite easy to remember, I find. Octahedral is 3 down, 2 up, and then tetrahedral is just the opposite, 2 down, 3 up. The other thing to note though is that, and you can probably see it from the way the diagram's drawn, the splitting energy of a tetrahedral complex is less than that of an octahedral complex. So in the similar way that the octahedral crystal field splitting energy was delta O, in a tetrahedron it's notated delta T, and delta T is smaller than delta O, and that's because, as we saw with delta O, you actually had d orbitals directly facing a point charge of a ligand, and in this case they weren't directly towards a ligand, but there was some interaction, so that's why it's smaller. And what's an important value to know is that the crystal field splitting energy of the tetrahedron is roughly 4/9 that of the octahedral splitting energy. And this is important later on because when we're looking at which geometry is more stable, it means we can actually convert a value of delta T to that of delta O, and then we can compare values. So now we know how the orbitals have split, what the d orbitals look like. It's time to know how to put the electrons from the metal in those d orbitals. And we've done this throughout the course, filling orbitals. And this is no different. It follows the same 3 principles, the Aufbau principle, Pauli exclusion principle and Hund's rule. So we'll be building up from the lowest energy. We can only have 2 electrons in an orbital with opposing spins, and they'll fill to maximize parallel spins before pairing up. So if we look at this complex here, so the titanium hexa-aqua complex, the Ti3+ ion has an electronic configuration of 3d1. This makes it a nice simple example. With an octahedral complex, we just have 1 electron to put in. So we see before it's in its complex, so in the spherical field, we've got the 5 degenerate orbitals with an electron. it then becomes the octahedral complex. The T2G orbitals get stabilised and EG get destabilised. So this one electron then goes and fills one of these T2G orbitals. And because this T2G orbital is lower in energy than it was in a spherical field, like before it made the complex, this leads to stabilisation. And we can calculate this energy as just 1 times the minus 0.4 delta O. So then the crystal field stabilisation energy, CFSE, is just minus 0.4 delta O. And this will be important when we're working out where electrons go and also what shapes they take actually. Let's take this with more complexes with more electrons, go through it and see what changes. So now we've got vanadium hexaaqua and chromium hexaaqua complex ions, vanadium 3+ and chromium 3+ then. And these have the 3d2 and 3d3 configurations. And these go into the T2G orbitals again, but following Hund's rule, they maximise the number of parallel electron spins. So you see with D2, we've got 2 up electrons in the T2G, and with chromium 3 up electrons in the T2G orbitals. And if we were to write this electronic configuration out, you'd see that it's T2G2 and T2G3. So it's more detailed than just D2 and D3. And in the same way we did in the last slide, we can write the stabilisation energy. So this time we've got 2 electrons in the T2G orbital. So this is 2 times 0.4 the delta O. So this equals minus 0.8 stabilisation energy. And then this time we've got 3 times minus 0.4. So we've got minus 1.2 delta O. So we can work out the stabilisation energy of each of these electronic configurations just by multiplying how many electrons there are with the splitting energy. And if we continue our journey across the first row hexaaqua complexes, we get to the manganese hexaaqua complex ion. And this throws up a bit of a problem because now this one's got an electronic configuration of 3d4. There are 2 possibilities of where to put this 4th electron. So we can either do what's called a low spin complex. So in this case, the 4th electron gets paired up in a T2G orbital. However, then we've got electron-electron repulsions, and we know they're a bit energetic, they're not too favourable. Or we can form what's called a high spin complex, and in this case, the electron remains unpaired, but it has to go into the EG orbitals, which are higher in energy. And that's also unfavourable. So then the big question is, does it go low spin, does it go high spin, and how do we work it out? Well, to end on a cliffhanger, that's what the next video is going to be working out.